Hi everybody, welcome back. In this video we're going to be talking about object tracking. This is a really interesting topic and a lot of fun to experiment with, and we hope you enjoy this demonstration. So first of all, what is tracking? Tracking usually refers to estimating the location of an object and predicting its location at some future point in time. In the context of computer vision, that usually amounts to detecting an object of interest in a video frame and then predicting the location of that object in subsequent video frames. And we can accomplish this by developing both a motion model and an appearance model. The motion model will estimate the position and velocity of a particular object in pixel coordinates and then use that information to predict its location in future video frames. And then we can also use an appearance model which encodes what the object looks like and then search the region around the predicted location from the motion model to then fine-tune the location of the object. So again, just to summarize, the motion model provides an approximation as to where the object might be located in a future video frame, and then the appearance model is used to fine-tune that estimate. So all of the code that we'll be using below is from the OpenCV API tracker class, and so we'll go ahead and talk about that a little bit more as we scroll through the notebook. So as a concrete example, suppose we're interested in tracking a specific object like the race car identified here in the first frame of a video clip. In order to initiate the tracking algorithm, we need to specify the initial location of the object. And to do this, we define a bounding box shown here in blue, which consists of two sets of pixel coordinates, which define the upper left and lower right corners of the bounding box. And then once the tracking algorithm is initialized with this information, the goal is to then track the object in subsequent video frames by producing a bounding box in each new video frame. So we'll talk more about this below, but before we get started with the code description, let's just take a look at the tracking algorithms available in OpenCV. There's 8 different algorithms listed here, and we're not going to go through the details of each one, but it's worth noting that depending on your application, one model might be more suitable than the other. For example, some are more accurate, some are faster, some are more robust to occlusions of the object being tracked. So that's just something to keep in mind as you experiment with the algorithms for a particular application you may have in mind. And then one other thing that's worth mentioning here is that the go-turn model is the only one that's deep learning based. And we'll talk a little bit more about that further below. So just as a preview to get started, we've got a test video clip here, and let's just play it 1 or 2 times. So you'll notice that early on, the car's appearance is relatively constant and its motion is fairly uniform. But as it starts to make the turn here, the perspective is more from the broadside portion of the car, and then also the lighting is starting to change quite a bit. And then now toward the end, it's getting smaller and smaller off into the distance. So those types of things are going to represent some challenges for some of the tracking algorithms. And as we work through this demo, we'll point out situations where one particular algorithm is having a difficult time due to factors like some of these that we've pointed out. So let's go ahead and take a look at the first code block in the notebook. Here we're importing some modules that are required, and then on line 10 we're indicating the file name for the video clip that we're going to process. And then here we're defining some convenience functions that will allow us to render bounding box information on the output video stream, as well as annotate the output video frames with some text. And then recall earlier that we mentioned the go-turn model is a deep learning based model. And this model uses a neural network to help us predict where the bounding box will be in a subsequent video frame. And so this block of code here is required to download that inference model. And then this figure here is a very high-level description of how the go-turn tracker is trained and used. So in the center here, we're indicating that we have a pre-trained neural network model, also known as an inference model. And it takes as input 2 cropped images, one from the previous frame and one from the current frame. And it uses the bounding box from the previous frame to crop both of these images, and therefore the object of interest is located in the center of the previous frame. And obviously, if the object is moved in the current frame, then it won't be centered in this cropped image because we're using the bounding box from the previous frame to crop both of the images. And so it's the job of the inference model to then predict what the bounding box is from the output frame here. So that's just a very high-level description of how that model works. So let's go ahead and continue on and take a look at the next code block. So this is where we're going to create a tracker instance, and we start by defining a list of tracker types that are available in the OpenCV API. And then depending on the tracking algorithm that we'd like to execute, you would just set the appropriate index here into that list. And since this is specified as 2, then we'd be indicating that we'd like to execute the KCF tracker. And then this if-else block is the logic that's used to call the appropriate class to create the tracker object. So in the case of the default, we'd be calling the tracker KCF_create class to create a tracker object of that class. So let's continue on to the next section where we're going to set up the input-output video streams. So here on line 2, we're passing in the video input file name to the video capture class, and that's creating for us a video input object. And then on the next line, we're going to go ahead and read the first frame from that video file, and that returns for us a logical as to whether or not that operation was successful, and then the second return value is the first frame from that video, which we'll use further below. And then down here on lines 13 and 14, we're doing a similar thing for the output video stream, creating a video output object. And this is going to be used so that we can annotate the output video with results from our tracking algorithm. So now we're at the point where we can initialize the tracker. And to do that, we're going to define a bounding box around the object that we're interested in tracking. And here we're doing that manually by specifying a set of pixel coordinates that define the upper left and lower right corners of a bounding box around the car. In practice, you would probably select this using a user interface, or perhaps use a detection algorithm to detect the objects of interest programmatically. But for demonstration purposes, we're just going to manually define the initial bounding box that identifies the location of the car in the very first video frame. And then next, we're ready to initialize the tracker. And so to do that, we use the tracker object that we defined above, and we call the init method for that tracker object, and we pass in the first frame of the video clip as well as the bounding box that we just defined above. And then once that tracker's been initialized, we can then process all the remaining frames in the video, and we can accomplish that in the following loop. So here on line 2, we're reading in the next frame from the video. And then on line 10, we're passing that frame to the tracker's update function, and that returns 2 values. One is a logical that indicates whether a detection was made, and if a detection was made, we get the bounding box coordinates for that detection. And then next we can compute the frames per second using these convenience functions in OpenCV. And then coming down to line 16, if a detection was made, then we'll call the draw rectangle function to render a bounding box on the current frame. Otherwise, we'll display a tracking failure message. And then further below, we annotate the frame with the tracker type and also the frames per second, which we calculated up above. And then finally, each time through this loop, we write out the current frame to the video output stream. So that's all there is to it. This loop cycles through each frame in the video clip, calls the tracker update function, and then annotates the frames accordingly, depending on whether or not a detection was made. So let's scroll down a bit further here and take a look at some results. So all of these results that we're going to take a look at here are output streams that were annotated with tracking results, and we're just going to play them back in the notebook. So as you can see in this first example, this is the KCF tracker, and I'm going to go ahead and play this, and we'll take a look at how it performs. So it looks like it's doing a fairly good job of tracking the car, a little bit off center, but still maintaining track on what's obviously the car in the video frame. And then as the car rounds the corner, it's doing okay. And then shortly here, we're going to see that it has a little bit of difficulty right here at the end. It drops track on the car. And as we go through other examples in this notebook, you'll notice that each of the trackers tends to have difficulty in different ways. So let's go ahead and take a look at the next example, which is the CSRT tracker. And notice that this one does a little better job of tracking the car with a bounding box encompassing the entire car and centered on the car for pretty much the first portion of the video. But then also notice that towards the end of the video, when the car is making the turn, the tracker is a little bit biased towards the front of the car, and then at the end of the video, it's kind of leading the car a little bit. So it doesn't drop track, but the location is a little bit off there towards the end. So let's go ahead and take a look at our final example, which is the GoTurn tracker, which is the only tracking model in OpenCV that's based on a neural network. So let's have a look. So initially, the tracker looks like it's doing a really nice job, like the other trackers, maintaining the bounding box pretty much centered on the car. And then also through the turn, notice that the bounding box, even though it's changing shape, is still really centered on the car. And even at the very end of the video here, where the other trackers had more difficulty, the GoTurn tracker is still able to maintain a fairly accurate position for the car. So out of these three examples, all the trackers were able to do a fairly good job near the beginning, but as it became more challenging, as the car is rounding the corner and going off into the distance, the GoTurn tracker was the most robust in this case, maintaining pretty accurate track throughout the entire video stream, right up until the end there. So we hope that gives you a good feel for how to exercise the various tracking algorithms in OpenCV, and especially the small amount of code that's required in order to get something up and running. So we really encourage you to experiment further with this notebook, try some of your own videos, and experiment with various algorithms. And we hope this was helpful to you, and we'll see you next time. Thanks so much.